trust especially between organizations and broadcast is going to be more and more important as we move in. So I'm glad you did the presentation. Thank you.
Thanks, everybody. Okay, let's get started. This is a report out of a project that we conducted in an outfit called ROS Research Labs, which is something we started at ROS last year, and I'm in charge of it. And the mission of ROS Research Labs is to rapidly learn and evaluate things that are new to us, it's the only R&D investment we make that explicitly isn't intended to end up in products, but it's nice if it does. And our main modus operandi is to build proofs of concept and do loadings from those and report out. So this is a report out of a project that was codenamed ERISA, and it was we basically put together a proof of concept around IS-10. So the objectives of that project were to learn about IS-10, authorization, and the related OpenID Connect, which is an authentication protocol, by building a proof of concept that simulated an infrastructure based on Dashboard, which is a very widely used control system, ROS Platform Manager, OpenGear, which is one of the most multi-vendor infrastructure solutions out there, with about 40, 50 partners and hundreds of thousands of frames shipped. And the things we wanted to learn was how hard is it, what impact does it have on performance, what architectures does it suggest, and what libraries are available. And this is all with a view to informing the appropriateness of this tech to making a better version of what we call OpenGear Protocol, OGP, which is a control protocol used by all of those partners and all those control frames. It's clear text, it's based on TCP sockets, it's not secure, it's not fit for purpose in this day and age, it's not cloud, it's not web or cloud scale. So those are the problems that we wanted to explore by doing this proof of concept. Other thing is that our business is different to a lot of web applications. Nobody cares if an email is 20 milliseconds late. If you do that with a frame of video, everybody cares. So that's one of the unique aspects of doing it in production that we were interested in learning about. So some context first. Trends in enterprise IT. It happens in enterprise IT before it happens to us in production, but here's a summary of how things have changed in enterprise IT. If there ever were good old days, then your network was defended by a well-defined perimeter. Things inside of it were trustworthy, things outside of it weren't. And that was the total story. Nowadays, because people can wander onto your network with their own devices, and you have multiple networks and offices and there's the cloud, it's a different story. So the modern approach to dealing with this complexity is trust nobody, trust nothing, and that's got a handy summary, a buzzword, zero trust. Why is it topical? Here's a quote that I'm very grateful to my friend Mike Palmer at Sinclair for getting as a John McClure, their CISO. Sinclair recognizes the importance of zero trust principles in today's technology and cybersecurity landscape, and is committed to embracing it and other security principles to secure our business. Sinclair aren't the only people interested in this. I work with a lot of vendors who have similar agendas. Zero trust by the numbers. If you want to dive into it, then I recommend these excellent publications from Cybersecurity Insiders. And they go back 3 years. And the reasons why people are adopting zero trust: they want to protect their security and their data. They want to prevent breaches. They want to prevent against threats from IoT devices and insiders. They need to be regulatory compliant. For that reads, get insurance written for them, and a number of other issues. But these are the top sort of 6. And how far along the path to adoption are they? This is quite interesting. There's kind of like an early majority and some laggards in this thing. But the biggest slice of this pie, they're actively partnering, they're doing it. It's on their near-term roadmap. The next biggest slice of the pie, just not ready. Don't have the skills, don't have the resources. And then the third biggest slice of the pie, we started implementing this, and the sad littlest slice of the pie, we've spent a lot of money, but we don't really know what we're doing. So it's happening. There's some dynamism about it in the industry. That's why it's topical. And here's the definition of what Zero Trust is. And this is another great publication. It's from NIST. It's their special publication, 800-207, and it defines Zero Trust as a collection of concepts and ideas designed to minimize uncertainty in enforcing accurate, least privilege, per request, I'm going to harp on per request later, access decisions in information systems and services in the face of a network viewed as already compromised. The bad guy is already on your network, is how you should be viewing things if you're going to adopt a zero trust mindset. This is a high-level architecture of zero trust, and you'll see how closely the proof of concept that we did adhered to this. Basically, the idea is you have an enterprise resource. It could be a camera-carrying robot, it could be a MAM, it could be a database. It's an enterprise resource, it has an API, and something wants to get access to it, a subject, and that subject could be a human end user via a web browser, it could be another service. And in order to get to the enterprise resource, it has to get through this combination of a policy decision point, which is yes or no, do you get access to the network, and a policy enforcement point, which actually creates the network plumbing necessary to make that happen. This is the key diagram. And here are a list of zero trust tenets. I don't have time to go through this in detail, probably to your relief, but some real things to grab are per session access. Have this concept of a session that's for which you have access, then after that session is over, you have to re-authenticate. Dynamic policy, real-time knowledge, dynamic authorization and authentication. Things are changing all the time. There's no such thing as set and forget when it comes to security and access control in a zero trust infrastructure. A zero trust network has these characteristics. There's no implicit trust. Just because the device is on the network, it doesn't mean it's trusted. Devices could be bring your own devices. They're not necessarily owned by the enterprise. They don't have endpoint protection on them necessarily, or agents that can ensure that their configuration is up to date. I'm going to move on from this. And this is a more detailed diagram of the architecture diagram I showed a couple of slides ago. And it separates things into a security control plane. And NIST calls the box below the data plane. This box here. NIST calls it a data plane. To make things clear, I've called it an operations plane because data plane has a different meaning in our industry. So what we have here is a security policy decision point. That's got an engine and an admin, and they are taking all of this real-time information from all these sources. Security and information event management systems, continuous detection and mitigation systems, AAA logs, and all of this information goes into this complex algorithm, the policy engine, which spits out a yes you can or no you can't answer, so binary output. And that gets relayed to the PEP, the policy enforcement point, which, as I said before, makes the plumbing to let this system access this resource. There are a couple of different ways of integrating this. This is probably the preferred way, where the policy enforcement point sits on the resource itself, very tightly coupled. That's sometimes not possible, especially with legacy equipment. So you might put legacy equipment in a resource enclave that you've secured by making this essentially a VXLAN or a micro-segmented part of your network, and you have a gateway to get to it that does the policy enforcement, and you might be clear text between gateway and the enterprise resources. This is an architecture recognized by NIST as zero trust. And then there's this final one where you have a non-enterprise system. You can't run agents on this, and it goes through a portal to get to the resource. So three fairly similar or related architectures, and we'll look at which of these stand up in broadcast. So now we're all experts in zero trust. Let's have a look at one of the ways of implementing it, which is the OAuth2 stack. It's a protocol suite. Anybody who wants a quick read and a very accessible way of getting up to speed on Zero Trust, I really recommend this. It's accessible on OIDC's website. It's a blog, and there are about 20 pictures in this cartoon, but this summarizes the problem. You know, in the bad old days, you've got shadybudgetplanner.com. I'm going to manage your budget, therefore I need access to your bank account. Give me your bank account username and password. And I promise not to do anything bad with it, snicker. This is a problem that OAuth2 tries to address. And here's an example of authentication using OpenID Connect. Here's my browser. I was blocked by the New York Times' paywall to get to an article I wanted to get to. And so it's asking me to authenticate. And you notice that I've got 4 different identity providers here. There's Google, Facebook, Apple, or the New York Times are doing their own, where I can give them my email address and password, which they manage. I elected to continue with Apple. And here's one of the key characteristics of OIDC, OpenID Connect. It redirects. So myaccount.newyorktimes.com is not going to take care of the identity management in this case, in my case. It's going to redirect to Apple. Apple, the browser then puts up this, this dialog where if I put my fingerprint on here, Apple will authenticate it's me and send an identity token back to the New York Times. And because the New York Times trusts Apple, it will accept that token as being John Naylor with a subject ID, and it will be able to proceed with that knowledge. And the key point here is the New York Times does not have my username, my password for Apple. Apple keep that secure. Okay, the objectives of OAuth2 is to enable just what you saw, so that I can have a budget planner that can access my bank account without knowing my bank account creds. That's got a lot of benefits. Mainly if that budget planner gets hacked and their database appears on the internet, my creds aren't there. They can't be compromised. There's a whole suite of specs called RFC 6749, which describe OAuth2. And let's move on. So here are some key concepts in OAuth2. We've already introduced the idea of a resource server. This is a resource that you want access to, like a MAM system. It presents an API to whatever protected resources are being served, and you need an access token to get into that resource. Access tokens are generated by the authorization server. This is a new player in the puzzle. Jed Deem, in his presentation yesterday, introduced this concept as well in one of his slides. Some of these implementations also fill the identity manager role. Identity manager, we saw the previous slide, or 2 slides ago. It provides authentication services, and it keeps the database of users, and it provides what are called authorization grants. Here's an identity token, and here's authorization to use whatever the resource you're accessing is. We have a client app, which is another separate entity in the picture. It's separate from the resource owner, it's separate from the resource server, and it's the means by which the resource is accessed on behalf of the user. We have a resource owner. When human, that's the one who decides, yes, you can access my checkings account, you can look at balances, but no, you can't make transfers. There's often a checklist of rights that you're going to access, and or that you, the resource owner, are going to provide access to, and those in the term of art are called scopes. We'll come on to those later. And the whole thing is, enabled by the use of tokens. These replace login credentials, they accompany every request, and that's how a token-based system implements and fulfills that Zero Trust Tenet of per request access validation. Tokens. JSON Web Tokens are one implementation, and they have a couple of different types. They're either authorization tokens, which provide access to a resource, or they're authentication tokens, like the one that Apple sent to the New York Times. They're identity tokens. There's an open standard method for representing the claims that they represent securely. And a JSON Web Token is simply an object that contains one or more claims. And they're often used as the payload of a JSON web signature, which allows the receiver to authenticate that the stuff inside the JWT came from who it says it's from and hasn't been tampered with. If you want to explore tokens a little bit deeper, this is a great resource. JWT.io debugger, you can go and put your own tokens in, you can edit them, you can apply different signature algorithms and see how that changes the output. A JSON web token is some JSON. It's got a header that says, I'm going to use the HMAC SHA-256 signature algorithm, and the type of the payload is a JWT, a JSON web token. Here's the payload. This one happens to be an ID token, so the subject ID is this, the name is John Doe, he has admin privileges, and it's issued at this time. And then the signature algorithm is here, and all of this gets turned into some base 64 followed by a dot, some more base 64 followed by a dot, illustrated here. Here's another access token. It's the one I used to get here on Monday, and it has a lot of the it's a metaphor, it's an analog to the claims that we're going to see later that IS-10 defines. Number one, we have a resource. This one is Delta 708 from San Antonio to Las Vegas to LAX, and that's the enterprise resource. It's the audience inside of a JWT under IS-10. It has an access scope, and scopes are critical to what I'm going to be showing you later. This access scope says that I can access seat 15A. It also implies that I can access the aisles, the toilet, the overhead locker. Remember what we said about dynamic policy being a zero trust tenet? When the fasten seatbelt sign goes on, I no longer have access to the aisle, the toilet, the overhead locker. I only have access to seat 15A. And the policy enforcement points in the guise of our air crew, or the flight crew, will ensure that I don't use the aisles or the overhead locker. There's a subject, that's just who the token is for. We're time boxed. I can't use this token tomorrow. I can't use it for any other flight than this one. And there's a signature. I presume I know that there's a signature in there somewhere. It's machine readable. Just for fun, an access token for a Southwest Airlines flight would have a claim represented like this, an access scope represented like this, where you can go in any seat. So you have a star there, whereas the Delta one says you have access to seat 15A. This is what a claim actually looks like once you look at it inside of an access token. This is something I'm not going to walk through, but if you just sort of maybe defocus on it, the top half of this is establishing a authorized connection with the resource server, where you're basically the end user and his agent is interacting with the authorization server to prove who they are. And then there's a second phase where the the client app is interacting with the authorization server to get access to the resource server before the end user finally gets plugged into it. So in summary, we've got the user interacting with the authorization server and potentially an identity manager first to authenticate themselves, and then the client app does the rest. It interacts with the authorization server to go and get a token that it can then present to the resource server, and the resource server's PEP, policy enforcement point, to actually get access to the resource. And the main points here are that the user doesn't interact with the resource server doesn't have the user's creds, the client app doesn't have the user's creds, authentication is decoupled from authorization. That's one of the key tenets of OAuth 2. Okay, we've got to the thing I was here to talk about, IS-10. The suite of OAuth 2 RFCs, they leave a lot of things defined as implementation specific, including an access token. IS-10 has done in my view, our industry, a great service by specifying all those gaps. So it says an access token is a JWT, and it's got some standard claims inside of it. And some are illustrated here. There's an issuer, a subject, an audience, an issued at. There's a time box, basically, around the validity of the token. And for IS-10, the time box is specified as somewhere between 30 seconds and 5 minutes, which is a way of delivering security. That's, you don't have long-lived access tokens. They have to be reissued which gives you a chance to revoke them and turn people's access off in a dynamic way. You can also define private claims in here. NMOS have done that by specifying the X-NMOS star claim. And what we did in the ERISA project is we defined one as X-OGPS. OGPS is the secure version of OGP. We've since rebranded that as something we've launched with the Open Services Alliance under the name Katina. Please go and have a look at the OSA's website for more information about that. Okay, IS-10 in Zero Trust architectures. Here's the proof of concept that we put together. So you'll recognize this is very similar to the architecture diagram that a Zero Trust reference architecture diagram. We have a subject. We've got the client app is kind of the enterprise resource. They're accessing resources that are protected by a policy enforcement point. And we've got an authorization service here that is doing authorization and authentication. So that's what we're going to build. And implementation details, the authorization server we used was KEYCLOAK. That's seeing a lot of traction in our industry. I haven't met anybody who's using anything else, actually. So the client backend was just a Node app. The front end was just jQuery and Bootstrap. And the resource server used KEYCLOAK adapters that are middlewares that allow you to validate access tokens. They call them adapters because they're not big enough to really be a full library. They're very lightweight, and our experience was that they were very, very easy to integrate into our Node application, and they have implementations in other languages, Java and so forth. So KEYCLOAK have done a great job in making it easy to use their authorization server. So OGP, yeah, we heard from Jed Deem yesterday. REST APIs, very popular. OpenGate protocol is not like REST. REST is stateless, OGP is session-based, the server can push. And the problem that we solved with that was, I've got 64 floating point numbers that represent my audio meters, and I need to send them to you 60 times a second for the next 8 hours. That's why we use a session-based approach in OGP. In REST, defining your endpoints in terms of tree structures comes naturally, and using those tree structures as a way to define your access scopes also comes naturally. In OGP, parameter structures tend to be flat. You can structure them, but they tend to be flat. So we had to come up with a workaround for that. And here's some examples of access scopes. So /star gives you access to everything, or /params fader1 gives you access to just this fader, or params /fader star gives you access to all faders. Hopefully this is making sense. To make OGP work with IS-10, we had to sort of retrofit a tree structure onto our data. Quick look at OGP's data model. A device has got commands, it's got some menus, which is the user interface, and it's got some parameters, and the parameter has got, it's got a configuration. You know, I'm an integer, I'm a float, or I'm an array. It's got some constraints that, you know, this integer can only take the values of yes or no, 0 or 1, and it's got a value. And then we recursively allow parameters to define maps of other parameters so you can get structures in place like this. And so what we did in our proof of concept, we mapped this onto a set of paths. This is what an OpenGate parameter looks like, defined in JSON. It's got a name, that's what appears in the user interface. It's got an object ID, which uniquely identifies it at device scope. It's got a type, a value. It's got a user interface hint, you know, present this parameter as a radio button toggle. It's not read-only, and that radio button toggle has got some this constraint on it, which is an integer choice. So you're either enabled value 1 or disabled value 0. That's what OGP looks like when you're defining device models. So the proof of concept scoping implementation, the claim is just the main API name, X-OGPS, and then we find some next level path names to basically model or replicate the device model, commands, menus, parameters, and then we wanted some scopes underneath this to provide further refinement. One by parameter purpose, so I'm either monitoring this parameter, I'm controlling it, or I'm configuring it, or by functional block, you know, ME1, ME2, etc. I'm going to demo the first today. So we created this sidecar file, which works like this. We have a map of the first two entries are params and commands. This is JSON. Then we have what we can monitor, which is a list of object IDs, what we can control, and another list, and what we can configure. And so the example scopes come down to something very similar to what we saw in the REST case, where /star is everything, just that fader is that one, and that's a command reboot, just a reboot command. And this is what they look like when represented as JSON. I've got three different roles here, a journalist, a technical director, and a chief engineer. You can see the journalist has got pretty thin rights. They can read the monitoring parameters, and they can read the control parameters. They can't touch anything else. A TD, they can read everything. They can write most things, but not the config. So they can write a fader, but they can't change the static IP address or the operating resolution that we're running at. And they can execute commands. A chief engineer can pretty much do everything. So the design of this policy enforcement point that we put in, the device model contains all the parameters. The access scope you have may not give you read access to all those parameters. So the job of the policy enforcement point, when it's delivering the device model to whatever client is rendering it in the UI, is to filter out those parameters to which the user does not have access. And likewise, any messages that come in say, change the value of this static IP address, unless the access scope says you have right access to that, those get returned with a 405, unauthorized. So demo time. Not doing a demo. This is a picture of Ottawa from a couple of weeks ago, where some violent storms took out the electricity supply for most of the city, including our lab for a while. And it made me rethink doing this without the benefit of a safety net. So what I've done is I've taken some screen grabs of a demo. I apologize for depriving you of the spectacle of me falling from the tightrope onto the floor, but it is what it is. So here's where we're starting. And this is a nice demo in terms of IS-04, etc., as well as IS-10. What we're starting with, all the machines here are virtual machines in this VMware facility. We're starting off with a DNS server running by 9 and an IS-04 registry. If anybody is in the crowd, in the audience here who helped write NMOS CPP, thank you. We love using it. It really helped get this project going fast. And what we've got here is a view into this registry, where right now the only thing in the register is the registry itself. So Arisa Reg Local is this machine. And in terms of what's in the DNS, there's some discovery in here. So that's our registration API is here, and our query API is here, and our authorization server can be found here. This really makes, once you've configured this, done a one conf, everything else it helps everything else be zero conf. So next we're going to start the authorization service, which is this one here, and it puts these things, makes these things available. This is what the KEYCLOAK console looks like. The realm that we used is demo, and it's got a few clients defined here. None of these, all of these are sort of out of the box clients. We don't have our client registered for this yet, which means it can't authorize our client to access the resource. That's a key consideration. Only trusted clients get on the network. and they have to be trusted by the authorization server before they'll do so. We have some roles defined. The offline access and UMA authorization, they're out of the box with KeyCLOAK. I think admin as well, but we defined these roles of custom, developer, and journalist. You'll see those later. And we defined some users, confusingly or non-confusingly, depending on your point of view, with the same names as the roles that they get given. We can federate users, so we could have plugged this into our local LDAP, but in this case, we use KeyCLOAK as an authentication server as well. So now we're going to turn on the ERISA client, the client app. So we just fire up that virtual machine, and we see that it's now registered. So this is the registry, and it's showing that we've got a client app here somewhere. There we go, erisaclients.rossvideo.com. So this is now discoverable by anything else. The client app is very boring at the moment because it's not registered with the authorization service, it's not registered with any resources, and so it's saying service unavailable. So let's give it something to register with. We're going to start our resource server here, which ERISA-resource is the name of this VM. And this then goes and registers itself with the IS-04 server, and this is how we got our scopes communicated. So we have there's this tags element in IS-04. You can put pretty much anything in it. We decided to put our scopes in here. So we use a tags dictionary to advertise the resource server's access scopes. This is probably an extension that's worth talking about within IS-04 and IS-10. Or there may be a better way to advertise access scopes. They are necessary, as we'll see later. So we're going to access the client. The client app has got an admin endpoint. So if you go and type in admin here, it'll try and do some administration. The first thing it needs to do is get authentication as an administrator. So it does this redirect to the authorization server and challenges you for your creds. And once we authenticate, we get access to the admin API or the admin UI within our client app. And here's a picture of it. So give my client ID a name, select a server to register with, and it's pulled from the authorization server the roles. So he knows there's an admin, a journalist, a custom role, and a developer role. And we have some buttons to press, register, deregister, update permissions. And then this client, it's a lab rat, it's a piece of dev code. We're logging what we get out here. And I can show you some of that. So you can see this is an access token, expiry issued at, authorization time, etc. Our audience are these different clients, which are all part of KeyCLOAK. Type is a bearer token. Whoops. Anything else interesting in here? Some roles for the realm access. I don't think there's anything interesting in this part. Here, we've got our NMOS access, so I can read the query, I can write the query, and I can read the registration API, and I can write the registration API. And I can do the same with the connection API. So we go back and we select a server. So we're going to give it a name and select a server to to register, which is the one we started earlier. And now we get this in this user interface where we've got the roles which are pulled from the server, and we've got the scopes which we pulled from the IS-04 server, and we use these to cross-tab them so that we can set up permissions for these different roles, for these different scopes, like this. So you can see the admin has got plenty potential rights. They're not allowed to write monitor. They can't write audio meters. That's as it should be, but they can do anything else. The journalist, they can read and write controls, but they don't have any configuration powers. They can execute and read commands, and they can look at the menus. Otherwise, they wouldn't get any user interface. So that's how we set it up for just these couple of roles. And this is the status that we got back, that we're registered. And now we can actually go and look at the operational interface in this client. So this is without the /admin at the end of URL. This is the actual device interface. And what this does is it renders the device model as a user interface. So each menu group appears here, and then the menus in the menu group appear there, and the actual contents of the menu appear here. And so you can see we've got some status menus, some config menus, and status has got product info, performance, and AV info. And all of this is read-only, which is, we're logged in as a client, as the admin role here. That's as it should be. So here's a snippet of the access token. It's X-OGPS. We can read, monitor, control, config, commands, menus, and we can write control, config, and menus. We can't write monitor, and we can execute commands. So that's the access scope summary of what the admin role can do. If we press the config tab, then you can see we've got some connections, orchestration, and audio sliders. This is a configuration kind of role, setting an IP address for our MOS host and our project server. The journalist gets less. So you can see their access token here. They can read a lot. They can write a few things. They can't write config, and they can execute commands. So when we go to the config menu, the ones that they don't have access to have been stripped out, and they just get access to this volume slider. And the reason why we're using status and config, even though this is more of an operation control, is that's how OGP was originally defined. I think we need to extend OGP to have more than status and config at the menu level. Okay, I'm going to come to conclusions. So what have we seen here? Zero Trust architecture applied to a widely used production operations protocol, that's OGP, implemented with OAuth2 bearer tokens constrained by IS-10. We learned a lot from this project, and we've recently retitled this effort Katina instead of OGPS, and we're working, we've proposed that as a project to the Open Services Alliance at a conference in New York last month as a multi-vendor interoperable control, configuration, and monitoring protocol that is designed to work on-prem and at cloud scale. We've seen there's some OneConf in here, so initializing those DNS text records, and also doing that dynamic dynamic client registration that we saw, where we were putting check marks on that cross tab of roles versus access scopes. But we also saw a pretty nice amount of ZeroConf, courtesy of the ISO4 discovery and registration. And we've seen fine-grained role-based access control. The admin gets a lot, the journalist gets what they need. The journalist cannot go and change the device's video resolution or audio sample rate, which is as it should be. That should be what a chief engineer does. Quick point about performance implications, something I worry about. Here's what happens in a normal setting today. So subject moves a T-bar. The front end sends a message to the back end, change the value of this T-bar. The resource responds, and the little LEDs like that get updated. Now do it in a zero trust framework, and you can see that the subject moves a T-bar, and the front end relays that to the client back end. The client may not have an access token yet. They may have to go and get one from the authorization service. And then they forward it to the policy enforcement point, which may not have the web keys yet, needed to validate it, so they may have to go back and forth. Finally, it will get to the resource, and the resource will respond, and then it will be relayed back. The key difference here is that non-zero trust, 2 computers, 1 IP route, 4 messages, proven accurate at a 60 frames per second scan rate. And you need a closed network for security. It's not zero trust. On the zero trust framework, we've got up to 5 computers involved. 2 of these, authorization and the policy enforcement point, they could be serving many clients or many users. There could be a queue or contention to get access to them. We've got 5 different IP routes, up to 12 messages involved, and that could make excessive jitter highly likely.
that impacts our integrity. We've kind of taken the fine sable painting brush out of the hands of our TD and given them a big fat chisel-tipped chips, given a big fat chisel-tipped Sharpie instead. We've compromised our integrity potentially, and that means we're not, we're not secure. Security is confidentiality, availability, and integrity. If, in order to maintain fine-grained access control, we compromise our integrity, then we've compromised our security. So there's a tension there, and this is something I think we need to talk about further and explore further as we try to apply zero trust to broadcast operations. Potential fixes to that, maybe we can do a 2110 on our operations plane so that you have guaranteed latency, and I'm sure that'll keep our switch vendors happy. Or maybe we could build jitter torrents into resource servers. Honestly, that's been done. We already do it, and there are plenty of patents around momentum models for transitions. Or we could look at some non-token bearer approaches, such as microsegmentation. Or we could just train people to use the auto button instead of the T-bar, and the problem goes away. Legacy equipments, I think we're going to have to put things inside the enclave. This is a model we saw earlier, and I'm going to wrap it up now.
All right, thank you, John.
Thank you.